This video is going to review some of the topics from digital electronics that we haven't looked at in a while and that I think are fair game for your EOC, at least a couple questions. A lot of what we cover in this class is sequential, meaning it builds on itself. So there's a lot of content that I don't think we need to review. So for example, we shouldn't need to review what an OR gate does or what an AND gate does, or how to take a Boolean expression and put together an AOI circuit for it, because those are skills that once we cover them, we are doing them the entire rest of the year. But there are some topics that we just touch on. In fact, a lot of them that we touch on in that very first unit, the first couple sections, that we haven't looked at in a while that I think are definitely worth reviewing. So we do touch on analog circuits a little bit in that early part of the course. The course is digital electronics, and so we mostly do digital circuits. We're dealing with the ones and the zeros, that VCC, and then opening and closing switches, because everything is either on or it's off. That's your digital circuitry. Analog circuitry are the pieces that deal with the resistors and the capacitors, and we don't talk about inductors in this class. Now, if there's one thing that I think might show up on your EOC that would deal with analog circuits, it would be Ohm's law. Ohm's law is this. It is V equals IR, where V is the voltage, I is the current, and R is the resistance. Resistance. Okay, and there's obviously other formulas with that, but I think that's the one that's like your moneymaker there. Now, circuit symbols for this, your voltage source is usually a battery, and it's represented by these alternating long and short lines. I always draw mine vertically, but you could see one drawn like this, okay? Somebody could just make it horizontal. The long end is the positive, the short end is the negative. So this would be like when you're looking at like a battery, it's got a positive and negative terminal on it. And so that represents the positive and negative terminals. So this would be like a battery, usually a DC power supply is what we would be dealing with there. And then resistors, I think you're probably okay with, because we have been using those in the digital circuits, but those look like that. They're just the zigzaggy lines, and it does not matter, like there's not like a positive and negative end to that. And then you have capacitors, and capacitors there's like different symbols for them, but sometimes there'll be two parallel lines that are the same length. You can also see one of those lines curved, and these will have a side to them, like a positive and negative. And a capacitor is like a temporary battery, sort of. It will hold the charge and then discharge it as it goes. And we use the capacitor to make the random number generator. It discharges I just did a review video on exponential regressions for algebra 2, so I'm in algebra 2 mode, where it'll discharge in like a decaying exponential. Okay, so those are the symbols that you would see in your analog circuits. Now, a series circuit. So series, if you think of a television series, you have episode 1, episode 2, episode 3, episode 4. Like they're sequential. You don't watch multiple episodes at the same time, at least not in the world I live in. So a series circuit is something like this, where you'd have your power supply, and then you would have your resistors all in a row, okay? And it doesn't matter if they look like they're parallel. So if somebody did this to you, and they're like, here's a resistor, and then here's another resistor. So you say, oh, those resistors look like they're in parallel. No, they are in series because they are in the same wire. And you could move those resistors around in the wire. So all this is just a wire connecting them. So if this were a physical circuit with some wires, like all you could do like with that is you could just bend the wire differently, and then put the two resistors, you know, next to each other, because you just like bend it, like, you know, well, that, you know, you'd have to like stretch the wire, but I think you get the idea. You can bend the wire anywhere you want. So a series circuit has the resistors one right after the other. In a series circuit, if you break one of the resistors, you would break the circuit and no current would be able to flow through the circuit. So nothing would flow because you essentially broke the wire. And if the wire is not connected, it's not connected. And it's not like if you broke the circuit like here, okay, it's not like the current would flow up here and then stop. Okay, so if there's no connection to the negative terminal, there is no current. So it's not like the current goes up the wire for a certain distance and then stops. Now, maybe relevant is engineers will see the current flowing this way from the positive terminal back to the negative terminal. That's actually backwards from the way it physically works. So if you're familiar with your science, you know that it's the electrons that are in the outer part of the atom. And so the electrons, when we're talking about the flow of electricity, it's the electrons that are actually doing the flowing. They are the things that are getting bumped off from atom to atom to atom, not the protons. So scientifically speaking, the current should be going the other way, and it should be the flow of negative charge, or like from negative to positive, but engineers do it backwards. And they picture current going from positive to negative, and it works just fine. The algebra and the science of it work fine. So that's a series circuit. A series circuit is sometimes known as what's called a voltage divider. So I'm making these up off the top of my head, which is extremely dangerous because the numbers might come out terrible, but you know, that's how we're rolling. So I'm going to say this is like a 12-volt battery. Okay. That's supposed to be a 12. There we go. And we'll keep it really simple. We'll say we have a 2 ohm resistor, another 2 ohm resistor, and then we would have we'll put a 6 ohm resistor. Okay. This is going to be some obscene amount of current. Don't touch the circuit. Okay, so what we mean when we say a voltage divider is we mean that 12 volts that you have in your battery here is going to be divided out so that over each of these resistors, so that as you move around the circuit, you're going to lose a certain amount of voltage. So the voltage, we call it like the voltage drop. And I've heard analogies of this is like a waterfall. So this is like you bringing the water up to the very top of the waterfall, and then it's going to fall down in stages. Okay, the bigger the resistance, the bigger the drop in voltage. And by the time you make it all the way around the circuit, you need to be back to 0. You need to have all 12 volts accounted for. And so a question you might be asked is to find like the voltage drop over like a particular resistor. And so the way that you do that is you've got to find like the total current. And so that requires you to know that when you add resistors in series, you just add them. So we would have, and then sometimes we'll do this in stages, but we'll find like what's called the equivalent resistance. So we have our 12 volts, and 2 plus 2 plus 6 is 10 ohms. So we have 12 volts, 10 ohms. And then we would use Ohm's law to say, okay, 12 volts equals I times 10 ohms. And then we divide both sides by 10. And we get 6/5, which is what, 1.2 amps. So what that means is that the current running through this circuit is 1.2 amps. And it's 1.2 amps all the way through the circuit. 1.2 amps. And you might be then asked, okay, what is the voltage drop over each of these resistors? And so now that you know the current, now you would go back and find the voltage drop. Well, the voltage is equal to the current times the resistance. We now know that the current is 1.2. The first resistor is 2, so that would be 2.4 volts. The second one would also be 2.4 volts, and then, so I'm going to make a mess of this. Okay. And then the last one, you would have the 1.2 amps times 6, which would be 7.2 volts. And then if you add them all up, 2.4 plus 2.4 plus 7.2, that is 4.8 plus 7.2, which is the 12 volts, and all 12 volts are accounted for. So that's one of Kirchhoff's laws, and it has to do with dividing voltage. And so you can break it down that way. Typically, we'll use a lovely soup of subscripts. So we would say, like, we'd call this like total current, and then we might call this like voltage 1. This might be voltage 2, and this might be voltage 3 to match up with like resistor 1, resistor 2, or resistor 3. So that's what it is to divide the voltage. Bigger the resistance, bigger the voltage drop. Parallel circuits look something like this. And we will typically draw them so that they look like they're nice and parallel. Okay. So they might look something like that. And in a parallel circuit, the voltage over each of these resistors would be the same. So if this is a 12-volt battery, then you will have a 12-volt drop in each of these resistors because they're all just connected to the terminal of the battery. Remember, this is all just wire. Okay, so this is a wire connecting into the terminal of the battery. This is a wire connecting into the terminal of the battery. And there's nothing between this end of the resistor and this terminal of the battery. It's just a wire. It doesn't, yeah, so that is the same here. Now, what's different in a parallel circuit is that the current divides. And so you have this like issue with the current. Now in a parallel circuit, if you were to break one of these resistors, the other two resistors would still carry the current because you would still have a complete circuit there. When you are combining resistors in parallel, you actually add reciprocals and then take the reciprocal of the sum of the reciprocals. Oh, it's so much fun. So let's take a look at now this kind of circuit is what would be known as a current divider. So this will take the total current and it'll split it up over the different resistors, and kind of like a similar thing where the more resistance you have, in this case, like with more resistance, you have like a bigger voltage drop. In this case, the more resistance, the less current. So you can kind of think of it again like a waterfall or a stream or something. The more resistance you have in a particular path, the less current is going to want to go through it. So let's take a look at a current divider. And again, I'm going to make up numbers. So this could be really ugly, but let's hope not. I'll try to make up nice numbers. So we'll stick with our 12-volt battery, and we'll do the same resistors. We'll do like 2 ohms, 2 ohms, and 6 ohms. Okay. And we might be asked, what is the current through each of these branches? Okay, what is the current? And so we start with Ohm's law. And first we have to find the total resistance. So this is the one that's not nice. So with series, you can just add them up. But in this, you've got to like add the reciprocals and then take the reciprocal of them. So PLCW uses some like horrible formula. Just deal with the fractions. So this would be, and you can use a calculator to do this, but this would be like 3/6 plus 3/6, which is 1 plus 1/6, so 6/6, 7/6, 7/6. And then we want the reciprocal, so that would be 6/7, and I don't have a decimal equivalent for that. A bunch of people have been texting me. Okay, 6/7. So this is about like 0.857 ohms. 0.857 ohms is our total resistance for this. So now using Ohm's law, we know the total voltage is 12. We are looking for the total current, and in this case, the overall resistance is that number. And so we divide both sides by that number. So we'll end up with 12 divided by 0.857. So, oh dear, 14 amps. Okay. So that's a 14, not an H, which if you're paying any attention, you know, because I said it. Okay. So that is our total current going through there. And then you might be asked, like, what's the current through each resistor, which I guess we didn't need to do that part, but we would have done eventually to verify Kirchhoff's law. So it's been a long day. So Ohm's law, we've got 12 volts over 2 ohms. So that means we have 6 amps through the first branch. We would have 6 amps through the second branch. And then that last one is going to be a little bit different. So we're going to have V equals IR. We're going to have 12 volts. And then that is 6. So we end up with 2 amps. And then the part that we were going to have to do anyway is if you were to add up 6 plus 6 plus 2, you get 12 plus 2, or the total current of 14 amps. Now, there are things to like notice about this. So notice that the higher the resistance, the less current you have going through there. That's that idea of that 6 ohm resistor is pushing back harder against the current. So not as much current goes through there. If you have equal resistances, you're going to have equal current going through them. And notice that putting the resistors in parallel actually lessens the overall resistance, where putting them in series increases the overall resistance for them. So that's like one of those things that's a little counterintuitive, because you think, oh, well, if I put more resistors in there, then I should have more resistance. Well, yes, if you're putting them in series, but not if you're putting them in parallel. Okay, now that's like a really straightforward series circuit and parallel circuit, but you can also see combination circuits. And I don't know what the chances are that you would see a combination circuit, but a combination circuit is some kind of circuit that has both series and parallel components to it. And so you might have like 2 ohms, 1 ohm, 2 ohms, 10 ohms, and 1 ohm. I don't know, like making stuff up. Okay, and you might be asked to simplify this circuit. Now, I honestly don't think that this is under the umbrella of digital electronics. This is analog circuitry. But who knows? Who knows? So to simplify this, you actually have to do it in stages, and I'm not going to go through that process right now because I think there's more digital stuff that's more relevant to what we need to go over. Actually, I think most of this review video is this piece right here. But what you would do is you would like see, is there anything I can combine? And in looking at this as someone who's done this for a long time, I see that I have some resistors in series that I can combine there. And so this would become a 2 ohm resistor, like we do this. So this is 11 ohms, this is now 3, and this is still the 2. And then I would look at these two and say, okay, those two are in parallel. I can combine those two. And I don't want to go through it, but it would be like 1 over 3 plus 1 over 11, and then take the reciprocal of that. And I know I said I wasn't going to do this, but now you got the 2 ohm and then whatever that is, like that number, the 1/3 plus 1/11, and then take the reciprocal, and then you could add that number to the 2, and that would give you your total resistance, or what's called like equivalent resistance. So as far as the battery is concerned, that's how much resistance you have in that circuit. And then a detailed circuit analysis, you would actually then need to find like the current through the whole circuit, the current through each branch, like the voltage drop over each resistor. Like you could really analyze the entire circuit there, but that would be a horrible EOC question because it's a very long, complicated problem, and it's analog circuitry. So I'm going to stop it right there. We've been doing this stuff for 20 minutes, and I think 20 minutes is more than enough to cover what you might see. So on to some other stuff. Universal gate design. So this is the universal, of course, means like everywhere. So in universal gate design, instead of having like AOI logic, you would have NAND gates everywhere. Everywhere in your circuit, every single gate is a NAND gate. And to do that, you need to be able to take your AOI gates and switch them over to NAND gates. So I stole this earlier today from the PowerPoint. So in AND gate, we can kind of go through how this works. An AND gate is like a NAND gate, but then you need to, let's start with the inverter. So an inverter just changes like a high to a low or a low to a high. Okay, so we have our inverter. To build an inverter out of a NAND gate, you would just run the same input in on both pieces of the NAND gate. And that would work. And when we did this in class, we went through the truth table to show, okay, like if you AND something with itself, you get itself, and then the inverter part is right there. Okay, so that's a one gate for one gate. Next simplest one is the AND. Well, an AND is a NAND, except you don't want it inverted, so you got to invert it back. So you would run your two inputs through a NAND gate and then immediately through an inverter. So kind of keep that in mind. With a NAND gate, the AND is the easy one. The one that's more complicated is how do you get NAND gates to OR for you? Well, you invert them and then NAND them together. And I don't want to go back through the truth table for all of that because we did do that. If you're just really want to know, you can go back and find that PowerPoint video for where this came from. But we did go through the whole truth table. So you would invert. And then the thing with your universal gate design is suppose you had something that was, let's say you were going to AND something together and you were going to AND something together, and then you were going to OR them together. Okay. So what you would do is you would take each AND gate and you would replace it with the equivalent. Okay, and then you have NAND gate. Oh, I don't know why I did that. Okay, and then we're going to OR them, which means we're going to invert them and then AND them together, okay? And then what you notice after you go through that, and you've got to go through every gate, there's really no shortcut to that. You go through every gate and you replace it with the NAND equivalent, and when you do that, you will see that you have a bunch of like back-to-back inverters. Well, there's no point in inverting something and then immediately inverting it again. That is a waste of gates. That's going to take you right back where you started. And so anywhere in the design that you have these back-to-back inverters, you can cancel them out. And so this ends up being that, okay, which actually is the same amount of gates that I had. And then the advantage to this is that now you only need one chip. So the AND gates and the OR gates are in different chips, the LS04, 08, 00, whatever. And the NAND gates are all in one chip. So now you've gone from two chips down to one chip, and your circuit's going to do exactly the same thing. Is it more design work? Absolutely. Is there a payoff for it? Yep, there's a payoff for it as well. You can also do universal gate design with NOR gates. So not as common as NAND gates, but we do cover both of them. And once you know one, you can figure out the other. So the inverter is exactly the same as it was for the NAND. So to do an inverter, you just take both inputs and run it through the NOR gate. Okay, so that should be easy peasy to remember. So it's one gate for one gate. You just run the input into both inputs. And then these are actually the same as well, as long as you like switch them so that they match. So with a NOR, OR is the one that's fairly simple. An OR gate, you want to OR them, but you don't want the negation. So you would put them in the NOR gate and then run them through the inverter to undo the inversion that you don't want. Okay, so yeah, there you go. So that's that. And then the AND is the one, like the one that doesn't match is the one that's more complicated. But the template is the same. So you invert them and then NOR them. Just like for the NAND, you would invert them and then NAND them. These ones, you would invert them and then NOR them. That's the kind of thing that when I'm teaching it, I'll have it fresh in my memory and I'll be able to do it. And then I go a couple months and I haven't had to do it. And then I don't remember it. I know there's a way to do it. And maybe I remember the inverter or like the one that matches. But I thought that was worth just going over, little refresher. It's not going to be on any kind of reference sheet. So I think that that is worth looking at. All right, we are more than halfway through this presentation, and I wanted to keep it fairly short. I really did want to keep this fairly short that you guys could watch it at home and get a decent review. Okay, so basic metric conversions here. Okay. This was a bit of an issue when we covered it. So there was a lot of getting stuff wrong because of it. So I wanted to go over like the prefixes, and you've probably noticed there are certain prefixes that come up a lot, and they're the ones that are the multiples of 3. That's your engineering notation. So like where would we see stuff? So I've seen a couple of mistakes with this where something was supposed to be like 220 ohms and somebody put in 220 kilo ohms because they weren't paying attention to the prefix. Well, kilo is 10 to the third. And so essentially this is 220 times 10 to the third ohms, which is 220,000 ohms. And so if you do that, if you make that kind of mistake, and then you wonder, why isn't my LED turning on? Because you put so much resistance in it that no current, like it goes back to the analog circuit from, I don't know, not even 10 minutes ago, like maybe 10 minutes ago. But the analog circuit, where if you've got so much resistance in that branch, none of the current is going to go there, or you'll turn off the current altogether. Okay, like you'll have such a massive resistance that like none of the current can make it anywhere. And so that's why we want to pay attention to that. The chances of you needing to do some kind of equivalent, I don't know. I really don't know. But let's say you've got something in, I don't know, because we just don't do a whole lot with this. This is really more the analog stuff where you might have, something in 20 picofarads and asked to change that to, that's supposed to be an arrow. I give up. You're supposed to change that to nanofarads. And so, yeah, so you look at your sheet here. Pico is 10 to the minus 12th. Nano is 10 to the minus 9th. So you're going to move the decimal point 3 places because they're off like 12 and 9 or 3 decimal places off from each other. And then the nanofarad is the bigger unit. So it should have a smaller number, because the bigger the unit, the less of them you need in order to measure what you're trying to measure. So if you need 20 picofarads, you do not need 20 nanofarads. That's a bigger unit. So that lets you know you're going to move your decimal point this way. And so you'd end up with 0.020 nanofarads. So I honestly don't know if there's a large chance that you would do this, but you will have your reference sheet that has the different prefixes on there. And as long as you're in the metric system, it's just a matter of moving your decimal place. So you've just got to think, okay, how many places do I need to move it, and which direction do I need to move it? You can get the number of places by using the exponent on the 10 to the. So if you needed to go from 10 to the 21st down to 10 to the 15th, that would be 6 decimal places. And then for the direction, think about, is the unit getting bigger or is the unit getting smaller? Okay, so a foot is bigger than an inch. So I don't need, so if I've got something that is 36 inches, because I'm transferring to a bigger unit, I don't need 36 of them. I need just 3 of them. So 36 inches is 3 feet. So kind of that's how I do it. I don't memorize every single metric prefix and the relationships between all of them to count that. It's just which units are bigger, which units are smaller, and then which how many places do I need to move that decimal point. All right, now, according to the baseline that I gave last year, there were not a whole lot of questions on number systems, but feedback that I got just said there were a lot of questions on number systems. So I don't know, but we'll go through that. So we'll talk about the different number systems, and I think this is the last thing that I wanted to go over. So we'll try to keep this to like 45 minutes video, give or take. So before we talk about other number systems, let's just be really clear on decimal numbers. How do decimal numbers work? We've worked with them our whole lives. This is the number system, except for when you do like a little side bar into Roman numerals, you use decimal numbers. So deci means 10. And what it means is that there are 10 digits. Those digits are 0 through 9. And so when you're counting, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you run out of digits. Enter this awesome thing called place value. So when you run out of digits, you start over again. So you start with a 0. But obviously that 0 is not the same as the 0 that came before it, because we have already counted up to 9. And so what we do is we kick over a decimal place, and that 1 has the value of a 10 because it is in the tens spot. And then the same thing happens when we run out of digits again. So we get up to 99. Well, that will reboot to 0, 0, and we kick over again into a new decimal place. In the decimal system, each place value indicates what the value of a number in that column will do. So we have the ones place, and then we have the tens place. And then the next time we run out of place, we have like the place values or spots. We have the hundreds, and then we have the thousands, and so forth. And that's where we get our place value from. This is why when you multiply or divide by a power of 10, so you multiply by like 100 or 1,000, all you need to do is move the decimal point. It's what makes the metric system really nice. Now, the pattern that we want to pay attention to, though, is this. 1 is actually 10 to the 0 power. 10 is 10 to the first power. 100 is 10 squared. 1,000 is 10 to the third, and so forth. Okay, that's what we mean when we say base 10. The base of the exponent. Okay, I just did this. The base of the exponent here is 10. So every place value is going up by a power of 10. Now, we have worked with the decimal number system our whole lives. So this is the kind of thing that you know without ever really needing to think that hard about it. The problem is that as soon as we switch number systems and we go into something that is, say, base 2 or base 8 or base 16, then we need to know how this works, because it works the same way for all of our number systems. So we have to just make that understanding really explicit. So let's talk about our next favorite number system. That would be our binary numbers. Prefix bi means 2, which means that we only have 2 digits to work with. Hence the whole digital thing where you have a high and a low. So 2 digits, 0 and 1. That's it. So when we start counting, we run out of digits really fast. Really fast. And so we have to start over. But when we do, we have to kick over a place value. And so we start counting up again, and then we run out of digits really fast again. And so we start over, and we kick up a place value. And this you guys are familiar with at this point, because we've done it enough, because you've counted up. And when we're analyzing our circuits, we're counting up in binary. That's how we can make sure we don't forget anything. The right-hand column always alternates 0, 1, 0, 1, 0, 1. The next column over will alternate in groups of 2. So we don't usually use those leading zeros, but it would go 0, 0, 1, 1, 0, 0, 1, 1. The next column over will alternate in groups of 4, 0, 0, 0, 0, 1, 1, 1, 1. And then the next group over here would alternate in groups of 8. Okay, and so forth. That's your binary number system, and you should be pretty good at counting at least up to 7. That would be your 1, 1, 1. Counting up to 7, because you do that in the switches all the time. And in a pinch, you should be able to go up through 15. Okay, so up through 15. Now, let's see, is there anything? Oh, the place value with these. So with your decimal numbers, the place values go up in powers of 10. In binary, you have the ones place. And then the next column over is the twos place, because this right here is the number 2. Like a 1 in the second column over is equal to 2. The next space over, if you, oh, right here, there it is the 4s spot. And then we have the 8s. And so like that's how we're counting up. Here's the consistency part. The 1 spot is 2 to the 0 power, because anything to the 0 power except for 0 is 1. The 2 spot is 2 to the first power. The 4 spot is 2 squared. The 8 spot is 2 to the third. The next spot over would be the 16s spot. And this is important because it allows you to convert from decimal to binary back and forth fairly easily. So if you had, say, the number 1101, well, this one is equal to 1. That's 0. This is a 1, but it's in the 4s spot. This is a 1, but it's in the 8s spot. So that is the decimal number 13. Okay, so you can convert. To convert the other direction, that is the thing where we would divide by 2, and like we just kept dividing by 2, divided by 2. I don't usually do it that way. So if I had, say, the number 35 and I needed to convert that to binary, I would probably look and say, okay, well, how many, well, that's like a big number. Like I would start by saying, okay, like that is 16. It's like 2 16s. So, oh no, we need the 32nd spot. Let's do a smaller number. Just because I don't want to go past, I don't know. I mean, we could, but let's just do a smaller one. Let's do 18. So we've got something in the 16 spot. So that would be like, we'll just say the 16 spot. And now I'm left with like a 2. So I have the 16 spot, the 8 spot, the 4 spot, the 2 spot. There's my 2. And so it would be something like that. That's how I would do it. I'm not sure that's a great way to do it. You could also do that repeated division where you do like 18, divide it by 2, and you look at the remainder, and like the remainder tells you like what the least significant bit is, and then you take the quotient and divide it again. So that is 8, and you look at the remainder. Oh, look, there's the 1, and then you take the 4 and divide it by 2, and so the remainder is 0. So there's that, and then you do 2 divided by 2, and that's 1, and remainder is 0, and there's the other 0, and then you do 1 divided by 2, which goes in 0 times with a remainder 1, and there's your leading 1, and you have to switch the order. I'm hoping you don't have to do too much of that. And it will be multiple choice, which means that you always have the option of working it in either direction. With a multiple choice test, you wouldn't necessarily have to carry out the mechanics of that. So there's that too. All right, almost done with this presentation. So hex and binary, and then I have and binary hex conversions. So I want to talk about hex. Hex is your base 16. So base 16 means you have 16 digits. And the digits go like this. They go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're not done. Those are our 10 digits. Then we have A, B, C, D, E, and F. And that brings us up through 15. Okay. And the same rules apply. So once you go past 15, okay, so we have like our E, F, and then you're like, oh, now I'm out of digits. Now you would kick over 1 decimal place, and this is the 16th spot. Okay, and so a 1 in that location is equal to 16 because of the whole place value thing. It's the same way decimals work, just with a different, like you're running out of digits at a different spot. Okay, and so like 1, 1 would be the number 17. Okay, in hex. Yeah, in hex. Now, the great thing about hex is that hex allows us to go in and out of binary super, super, super easy. And so what you do is you have like most of your digital stuff is done in what's called a byte, which you are familiar with because you know like your memory comes in like megabytes and gigabytes and stuff. So you've heard that word byte. A byte is just 8 bits. It's 8 of these little 1 or 0 bits. And what you can do is you split them in half. Those are actually called 2 nibbles. 2 nibbles make a byte. 8 bits make a byte. You can't make this stuff up because engineers have a messed up sense of humor, but that's what they call them. They call them nibbles. So let's say you had the hex number like 1, 1, okay? What you would do is you would take each 1 and you would break that up into its binary equivalent. So 1 in binary is 0, 0, 0, 1, and then you'd have 0, 0, 0, 1. And so your binary version of hex 1, 1 is 0, 0, 0, 1, 0, 0, 0, 1. And you can just take each of the digits separately. And it makes for really, really easy conversions. And usually in engineering, you will use those leading zeros, again, because everything is done in bytes. And so you don't want to leave like unoccupied territory with that. So if you had something like A3, okay, and you had to convert that to binary, you would just do A, which is 1 0 1 0, and then 0 0 1 1. So A3 is 1 0 1 0 0 0 1 1, and you could go the other direction. Suppose you had 0 1 0 0 1 1 1 0. Okay, so that's your binary number. You could just take the first nibble, which would be 4, and then the second nibble, which I think is what, E. So that would be 4E. So that's how you go back and forth between your binary and your hex. You like split it. And what that means is that you only need to ever convert up to the number 15, and you can get way, way, way bigger numbers without ever memorizing anything past F, which is really nice. I took a course in microcomputer programming, which is predominantly in HEX. So we did a lot of HEX coding, just with the ones and the zeros, but we weren't dealing with the binary all the time. We were dealing with the HEX, and we used essentially HEX as a short for the binary. And that brings us to our final slide. It's going to be longer than I thought it. Octal is base 8. And so this one I did not use. I used HEX all the time. Like HEX was what, like, but that was probably my program. It was the specific technology we had. So we were using Motorola devices, but if you were in like a different college, a different program, a different business, they might use different technology, and that technology might use Octal instead. So an engineering course is going to cover all of it. In Octal, it's the same principle. You are limited to 8 digits. So once you get to your 8th digit, so it'll be 0 to 7, you're going to run out of spots, and then you're going to start over. Okay, with the 8th spot. So you have the 1s spot, and then this is the 8th spot. Okay, and then this would be, the next one out would be the 64s spot. Okay, for me, that's like a lot more awkward. But you can do similar things with this, with your octal to binary conversions. So you can, but you would just group them in groups of 3 instead of groups of 4. So the hex, you're going to do like the 2 little nibbles, and you can go in groups of 4. But like for this, if you had, say, octal 7 5, you could convert that to binary by doing 1 1 1 1 1 0 1. So you could convert octal 7 5 into binary 1 1 1 1 1 1 1. Long day. So you can convert that way. Now, the other kind of thing you might be asked to do is you might be asked to go from, like, say, octal to hex, which you could probably do. I think I would do that by going through binary. So I would take like 7 5 in octal, convert that to binary, and then I would do this little number and put the leading zeros in, and then use my nibbles to convert it over to hex. So this would be 3 1 1. What is that? A, B, is that C, D? Oh gosh. 10, 11, 12, 13. It's 13. So A, B, C, D, 3D. Okay. 3D. I think I would do that because I think binary is the faster of the 2 ways to do that. You might be asked to go from like octal or hex into decimal. I mean, I think realistically, people aren't going to go from octal to hex. Like, there's only certain kinds of conversions you're going to do out in industry, because like you're either going to be committed to working in like a particular number system, and you're going to minimize how much in and out of that number system you have to do. But I wanted to make sure that I reviewed that in more detail than I reviewed it last year, just based on the feedback. Nobody told me what the questions were or anything. It was just like, man, there were a lot of number systems on that. And so I was like, okay, we covered it, we reviewed it, but like we can review it a little bit more. So I don't know what, again, like I haven't seen the exam. I don't know what exactly is on it or anything like that, but I figured let's get this reviewed a little bit better. So, all right, so there we go. So I got it in under 50 minutes. Make sure that you do watch this before you, well, if you've got this far in the video, you have watched it. Hopefully you haven't taken your EOC yet. As always, you guys know where to find me if you've got questions or you got something else that you would like to go over.